everybody. I'm Justin from Toolpath, and I'm here with Yavuz, the CEO of ModuleWorks. And today we're going to be talking about whatever topics we feel like in terms of Toolpath generation. Say hi, Yavuz.
Hi, Justin. Nice meeting you.
Yeah, nice talking to you again. Thanks for taking some time with me today. So, why don't you give us just a very brief history as to how you got into the Toolpath business? Like, what was your path into that?
I'm almost 30 years in that business now. I started mid of 90s here in a small town called Aachen in Germany. They call it the Mecca, the center point of machine tool research. I used to work there as a research assistant on machine tools and vibrations and chatter. And I met a gentleman who gave me some programming projects. So I was the developer for him, writing some algorithms for CAD/CAM, and enjoyed what I'm doing. And that led me to develop the 5-axis algorithms for very complex shapes like blades and engine ports, etc., which eventually became, in the 2000s, the ModuleWorks company. And it was an interesting journey, and I enjoyed every bit of developing and working. And now we are almost 400 people, and I'm managing the business side of the company, but still my heart beats still for the technology.
You started in hard mode there. The first toolpaths you wrote were 5-axis toolpaths?
Yes, that's correct.
Having to deal with all the kinematics and everything?
Yes.
Wow. Okay. When you start thinking about like coding a 5-axis toolpath, do you think about collision avoidance, or how do you break down the way you want to design like a particular toolpath?
Honestly, I was a bit triggered by the initial customers. So the initial customers were the U-boat producer in North Germany, and another customer would like to machine a first electrical car prototype, the complete body of the car with more than 200 individual trimmed surfaces. And I was working on a 486, right? So you can imagine
486 processor.
Yes, exactly.
Yeah.
So, I mean, imagine machining maybe a 4-meter part with hundreds of surfaces, and then I'm starting from zero, from nothing, and there is no CAM system in the world at that time who could machine that in 5-axis continuous. And my task was just do it, right? So what you end up is, as an engineer, you say, okay, what is doable? I mean, how much horsepower I have with my 486? So I resisted the attraction of developing a collision control at the beginning, because it was just not doable at that time, right? With the accuracies, you had to machine the part with the surfaces. So what we did is we stayed normal to the surface, tried to be, perpendicular and away from the surface geometry, offering some tilting options, and we introduced on an exhibition a new naming for that. We called it, we have a collision control. It's called visual collision control. So you look at the simulation, and if it collides, then you go back, right? And people said, yes, that's practical. So we introduced the visual collision control because we could simulate the kinematics, the machine, the head. It didn't have any real collision control, but it was good. It was a good tool at that time. And that was the start. People were able to machine these things. And we teach them how to use the visual collision control and the options. And of course, it took weeks to program a single part, right? Like the first engine part I programmed, I think I spent almost 2 weeks just to program a single engine part with the software I just developed. So it's not the programming of the code, it was just programming of the part. And today, with our current algorithms, you just press a button, 10 seconds later, you have a full collision-proof port engine machining at nothing, right?
There's a whole bunch of irony in that story. First is, I suspect that the processor in your earpods right now has more horsepower than the 486 that you were using for those 5-axis toolpaths. And another one is that you're 100% right. I had never thought about like manually controlling the tilt. And I just completely take for granted now that like it's all automatic and everything. There have been a few moments though where I'm like, oh, I just want to grab it and control it. And And so all that automation has sort of ironically removed the ease of which, like when there's just one moment where you just want to control it really tightly. So I think that's very interesting. Okay, so your first foray into 5-axis was all about generating the toolpath itself, and you just sort of left the crashing up to the responsibility exercise for the reader, I guess. What kind of toolpath was that you built?
At that time, we were focused on finishing toolpaths in 5-axis. So basically, the roughing would have been done classically with 3-axis or indexed 3 plus 2 axis using the normal algorithms. So it was the finishing toolpath or pre-finishing toolpath with the offset. And the unique point at that time was that the CAM systems on the market so far were coming from the era of APT, where you define a drive surface, some check surfaces. So it was almost like a parametric designed, tailored toolpath, but with the guidance of some surfaces. So that was the thinking. So basically all CAM systems who integrated that into their CAD/CAM environment ended up providing so-called flow line toolpaths, where every surface has a U and V domain, which spans a surface. And they were just following these U and Vs because people believe that you design a surface in a way you want to also finish it later, right? And they didn't know any better. So basically it was a limitation of CAM systems. They thought it's how it is. But the first customer had these 200 surfaces and they wanted to machine the whole part. You cannot machine 200 surfaces individually. So, and you cannot join to.
They wanted it to like continuously.
Yes, right? you need to machine that continuously. And there were some CAM systems who tried to connect two surfaces, stitch them together to make a unified UV domain. But for a shape like a body car shape, car body shape, you cannot just, merge everything to one single surface. So I said, okay, let's take the challenge and create a slicer. And the beginning was actually in 1996. I developed for a Swiss company a slicer where they just wanted to get Coca-Cola bottles in CAD model, in surface model. They didn't have volumetric modeling. And they wanted to size it for family size Coca-Cola and small size and large size. But they needed to have their design kind of calculating from it the volume of the design such they can scale it accordingly. So basically they needed a tool that would calculate the volume of a surface model, which is not a volume module. And that required to calculate a volume. What you do is you just slice and you calculate the area of each slice and you accumulate that, right? So basically, I had developed in 1996. At that time, I was working in the US for a company, but that was something I was doing as a side job. The volume of geometries, and this volume calculation required the slicing of the model, like you would do today for additive manufacturing. And I sliced it in different directions and checked the plausibility of the result being correct. And that taught me a lot about Nurbs geometry. So I invented my own Newton-Raphson extended method, because the classical Newton-Raphson did not work very well. And fortunately, the Nurbs geometries were quite well behaving. So I didn't have noise in the data. So with a few tweaks, I was able to get a very efficient slicing. And it was at that time even 386, not 486. So, and then I transferred this further to 5x machining. I said, okay, I have 200 surfaces. I slice everything. I got a curve. And I stay normal to the surface by just looking at the UV. And that was the beginning. So the volume calculation for slicing became the 5-axis engine I developed.
So you were slicing, but you weren't slicing into a mesh. You were slicing still into parametric Nurbs planes, I guess?
Yes.
Okay. So do you think today most 5-axis toolpaths work on continuous parametric geometry like that, or do they resolve down to a mesh first?
I mean, half. I think more and more it's all mesh-based, right? Because of the convenience of mesh. But the Nurbs still gives you an unprecedented accuracy, right? We use the mesh algorithm with our friends from the ultra-precision machining domain. They build machines that can create toolpaths in sub-nanometer. I mean, not sub-micron. I'm talking about sub-nanometers. They have some optical devices to measure the quality of the optics they do, and then they do the last compensation finish, etc. And they realized they cannot go farther with mesh. So they had to work on Nurbs, and even the Nurbs had to have a super quality. So, and we realized that the Nurbs is possible because it converges very nicely. So if you go from a micron tolerance to a nanometer tolerance, it's 3 magnitudes. It just takes maybe 2 times longer, but not 1,000 times, because I end up on the UV domain just adding a few points more, because I know locally where I am, right? I'm not looking the solution in 200 surfaces. So Nurbs has its own advantages, but it has also significant challenges. So for that reason, the next generation toolpaths are always mesh-based, where you can do much better collision checking, and you can do much better planning. You can do things like geodesic propagation of finishing toolpaths, which are not easily doable in Nurbs geometry.
And of course, that powers the geodesic ModuleWorks toolpath,
yes.
Right? So that one is mesh-based.
That one is mesh-based. Okay. And we spent almost 20 years on that, just on that toolpath. Even on mesh, having a geodesic working well, although everything is well-defined, you have just triangles, very simple primitives, right? It was 20 years of work, and we are still improving it, right? And in Nurbs, I don't think it's feasible to do that on Nurbs. So what we do today is we calculate on mesh, and we reproject everything back to Nurbs to get the quality of the Nurbs, but with the planning capability of the mesh.
This is a bit of an aside, but it always continues to amaze me how heavily the CAD/CAM world intersects with my prior life doing CFD optimization. We almost exact parallel there. Early on, I had to do a lot of geometry work because when you're trying to optimize the shape of a wing, you have to change these airfoils, right? And there are some people who want to work in the parametric space and some people who want to work in the discrete mesh space. And exactly the same thing ended up happening is that as these two things evolved, you could parametrize the shape however you wanted, but to get the accuracy, you always project the discrete space back down onto the continuous space. So even if you're working on a mesh. So that's very interesting. 20 years to refine the geodesic toolpath. I have some sense of how much work goes into that early on in Toolpath. Faye, one of the developers at Toolpath, and I worked on a Deburring toolpath. This would be 3-axis only, far, far inferior to the ModuleWorks Deburring one. But we really, early on in Toolpath, we were working purely with mesh-based geometry. So we didn't have any continuous geometry. And to get a really nice, smooth behavior over that mesh was very, very challenging because the meshes have all kinds of weird noises and you get these super tiny triangles. And so we ended up coming up with a shadow averaging approach that gave us very, very, very nice looking results. And that actually made it into part of Faye's PhD thesis. So I have some appreciation of how difficult it is to work with mesh data. And I think the human brain is so good at noise reduction when it's looking at a mesh. We just look at it and we're like, oh, it's very obvious the tool should be pointed this way or that way. But to get a numerical result that doesn't have the tool jumping around like that is very, very challenging.
Absolutely.
Okay, so 50-50, you'd say it seems like some toolpaths are purely parametric, some are purely mesh. And the most advanced ones today are probably starting in mesh space and then deriving final accuracy by projecting the result back down.
Yes, absolutely.
Okay. All of that work, and we graduate from 386 to 486. It's really easy to take for granted how much compute power we have today compared to what we did 30 years ago. And yet we still seem to always take forever to compute the toolpaths. So what drives the computational cost in a toolpath? Sort of very broadly or even specifically for something like geodesic, where's all that compute time going?
That's a very good question. I mean, first of all, the expectation on toolpaths are quite diversified. So there is not one toolpath style. Like it's not like everybody wants to do a parallel lace toolpaths, and you could just work on this and optimize to death by parallelizing that, right? So basically, because of the pipeline of toolpath calculation, like you need to calculate the pattern and you need to project it, you need to do collision checking, you need to check, maybe the in-process stock evolvement and so many things. There are so many stages where you get easily the limits of parallelization. So you cannot use, because computer get faster, but they get faster mostly by adding more cores, right? But not every in each stage of the toolpath calculation is parallelizable. So basically, sometimes you need to do things sequentially, right? That limits you. And at the same time, the expectation on toolpaths get bigger, right? So basically, maybe in the past you would put in maybe 20 micron tolerance, maybe you put together 1 micron tolerance, and now you have maybe a tool shape which looks like a barrel, and you want to have a collision checking very accurately with the arbor. So these are all the things or your links in the past you accepted that it lifted to the clearance plane. Now you want to have a small lift and check local collisions against the actual in-process workpiece and the target geometry, and then do a very smart blend spline link or whatever. So basically the expectation on the toolpath smoothness, quality, collision awareness, etc. increased significantly, such we use most of the computation power we have to work on these elements, right? And but still we have the ambition that no customer should wait more than a few minutes, even for the largest and most complicated toolpath, right? So if they wait for an hour or so for a toolpath, then we have to do something. So that's our passion on the toolpath calculation. Most of the toolpaths should happen in just a few seconds, right? For normal tolerances, normal parts. Complex toolpaths maybe in minutes, but nothing in hours, right? It is possible. It's technically possible. But you need to go back and readdress all your design choices on the architecture and keep adapting it, right, to the new architecture and to the new methods.
Compute cost is a topic that I have to pay super close attention to, because Toolpath pays for the compute for our customers. So we're in a unique situation, but also because we're trying so many different toolpaths. So I've had the benefit of working with you and your team to take some shortcuts sometimes when we just need an approximate toolpath. If we're trying to figure out volumetric matches or the rough estimate for how long a finishing toolpath will take, we don't need high accuracy. And so it's been very interesting when you're like, oh, we'll just turn this parameter down, and it dramatically cuts the compute cost. I wonder if in CAD/CAM, if there'd be value, like as you're planning out complex parts, like to dial everything back and then have a button you press, be like, okay, I'm happy with this. Now go refine the toolpath for me.
Yeah. I mean, we had an interesting experience in the dental business where 15 years back, when we started the journey by developing some adaptation of our toolpaths for the dental market, we were happily cutting the parts. And then if it doesn't work for some reason, it was like a disaster, right? Because there's a patient waiting for his crown and he doesn't get it, right? So, and we realized that there is not a CAM operator. So at the end, the toolpath always have to work. So the first thing we did is we got a server and put more than 1,000 dental indications. And every single night we run all our toolpath engine, and we were developing every day new code into it against that one to see if there is any exception being thrown. And in case of an exception or wrong result, we would just go and find a solution. Like if A doesn't work, then the code should do B, because we can never say we don't machine that part. We always have to machine it. So we figured out that by just changing the tolerance, things just can work or cannot work. So we called something called a shake tester, where we started changing the tolerances. We would shake the tolerance and rerun the same test thousands and millions of times until we find all the bugs we could fix in the exceptions. These are numerical inaccuracies, etc. And at the same time, if an exception happens, we would catch the exception internally, recalculate everything with a slightly different tolerance, and then still give the customer the good solution. So the customer would just wait a few seconds longer, but he gets the solution. So in that journey, we realized that stability, that you have to be 100% correct. Even 99.9 doesn't cut the deal because there is nobody going to proofread it, right? It's getting machine. It's like PDF file, laser printer, print button, right? That's the expectation. So once this is solved, we thought now the world market is open for us. We could take over and do the stuff. They said, no, it's not there. You are not there yet. We said, why not? Okay, it takes 5 minutes to calculate a crown. It was a full 5-axis from 2 sides and 7-8 different toolpaths with 3 different tools. We said, okay, what do you want us to do? Okay, make it faster. Okay, we came back. We were under 1 minute. We said, are you happy? He said, no, you are not there yet. We brought it down to 30 seconds. They said, you are not there yet. So at the end, we brought it down to 4 seconds. So basically, the complete crown calculation was 4 seconds. And afterwards, I asked why they needed this 4 seconds. They said, look, if the people press the button to start the production, they want to hear at least after 4 seconds that the machine starts running, like the laser printer, right? I was kind of, okay. So, but that gave me the confidence that if the customers are backing that, right, we have a very good team. We have so many bright people. If we say, that's the only thing you need to do, make it damn faster, they can do it, right? But
if only you had asked that question at the start, you could have just issued a roughing toolpath and finished the calculations while it was making some noise.
Yes, one of the partners actually did that. He never complained about the speed because he started the roughing toolpath. But he was also the machine tool builder. The other customer was an independent CAM system. So he had to work with all machines. And so he could not interfere with the architecture of the system. So he didn't have the option to split the toolpath and send a second toolpath afterwards. But that was very good. And I asked him after this 4 seconds, how is the competition is doing? And they said the competition is still in minutes. So that's the reason we are selling the best, right? So I was like, okay, come on. But that were the situation. As an early company, you try to always, like the challenge and jump on it and do something. I think today we might need to maybe prioritize better what we do and where we invest our time and money, right? But that's a good anecdote. I have to smile when I remember the times.
We have that same problem at Toolpath now. It always has to be faster. It's never fast enough because people are sitting there waiting. But I had a customer recently tell me an anecdote that I'm really proud of. If you're just programming one part, then the wait time of even 30 seconds feels like an eternity. But he got an RFQ for like 40 parts, like 40 unique parts. And he uploaded them to Toolpath, got answers for 40 parts. And when it's processing 40 parts in parallel, all of a sudden 30 seconds doesn't feel so slow. Got the answer. And within like 20 minutes sent a response back to his customer. Like a quote. And the customer got back to him and said, did you even look at our parts? How could you quote this that fast? So when you're processing like 40 parts at a time, people are pretty tolerant of having to wait a few minutes. They're like, oh, okay, yeah, I can understand it takes some time. If you're processing one part, though, having them sit there and wait for the entire calculation of the AI to give them an answer is like unacceptable. And so we always have to sort of drive that cost down.
But I think there are ways to visualize the calculation. I think people like the computer doing number crunching, doing something. Like imagine you would let the user press the button and you would immediately do a volume calculation and do a first very empiric something where we put a range. You say it will be between $100 and $200, right? And then you would start that and you would narrow the band, right? So you get the accuracy. So I think people love this kind of things. The computer is working and it's giving you better answers to time trade-off, accuracy, etc. But I think you are doing a great job. I mean, calculating real toolpaths for quoting and at the quality of, you can go even to the machine and machine. This is incredible. I mean, this is going to be the biggest game changer. That will be the ChatGPT moment, right? If people start adopting this technology.
That's the goal. Our big focus right now is on providing, I think what really makes ChatGPT compelling, I mean, the core of the technology is amazing. Although, fun side note, nobody understands how these AIs work. Like mathematically, they do not understand why the AIs work as well as they do. It just became an emergent property of one of these big neural networks. And they were like, oh, well, if we make it even a little bit bigger, then it starts having more reasoning. And so they just keep making it bigger and bigger. They're starting to understand how it works, but like fundamentally, this behavior of these GPT models was not an expected outcome. But what makes them really, I think, like fundamentally game-changing is the way you interact with them. So you ask ChatGPT something and it gives you an answer and you like it or you don't like it and you say, no, refine this or improve that. And it's that interactivity and that cycling that makes the technology feel really magical. And that is our big focus on Toolpath now. I like to say that you should tell Toolpath how to program, not the other way around. I can't imagine anything worse than like a future where the all-knowing AI just tells you how to make every part and you have no say in it. But giving people that control and giving them that interface to express their intent in a meaningful way for the AI is a big challenge and one of our core sort of development areas right now.
I mean, imagine that people would drag and drop the part on Toolpath Labs framework and then just interacting by talking to you and saying, oh, just use this other tool, or, try to check if instead of aluminum we use steel for that part or whatever. That could be, I think, quite a nice way to connect it to the ChatGPT, because this whole verbal interaction and that you get the feeling that ChatGPT really understands you. Sometimes even among your family and friends, you don't have the impression that everybody understands you very well, but ChatGPT tends to understand you very well, where you are really appreciating that. I think the software, legacy software is always, you have to click always the right button to get the right result, right? So it doesn't understand your intent. And if you could connect that phenomena with your engine, I think the people would love it.
We are looking at linking an LLM to Toolpath, so stay tuned for that, but no promises there. Let's talk about the Deburring toolpath that you have a bit. I mentioned that we tried to write our own early on, well before ModuleWorks and Toolpath started collaborating. But I know that you built that toolpath after like watching some customers struggle in a shop visit, right? So walk me through like the birth of that toolpath and what makes it unique, what makes it special.
So I was visiting a friend of me who was at a job shop owner, and we're talking about what he's doing, his people are doing, and I see a young gentleman, he's most talented CAM programmer, sitting at a CAM system, and he had hundreds of lines on his screen. And I said, wow, what you are doing there? He said, oh, I just projected all the edge curves of all the geometry to a plane. And then I generate a 2D toolpath on them. I reproject everything and clip everything against the part. And that's how I do a deburring toolpath, because I don't want to manually deburr the part. I said, okay, how much of time you are spending on this? He said, the half day I'm spending on just this part, deburring toolpath, right? So after I've seen that, I walked to the office back and said to our people, let's develop a deburring toolpath, because people should not abuse contour toolpaths and projection and spend half of their days just to do things that we should be doing. And I realized that the classical CAD/CAM systems, they had contouring and pocketing and all these classical bits, right? But a lot of people were just abusing or using these things for other purpose, right? If you just go to job shops and look what they do day in, day out, and see how they work around things by tweaking some things with some existing something else, you get so many ideas, because these are all the things you would expect in 2025 from a CAM system saying, okay, please do deburr all edges for me, right? That's the level of complexity you would like to, deal, and not starting doing some CAD work.
And now with Toolpath, we even go to a higher level and we talk about setups and features and tools and not specific.
That's very big. I think what you do with fixtures and setups is, I think, one of the biggest blind spots in CAM systems. You are basically left alone by dragging some fixture geometry, tweaking your setup, and finding out how you do it, and then simulating it, and so on. It's a lot of time waste, right? Even if the toolpath calculations would be instant and correct and whatever, you still have to do what I call the process planning with the setups, right? And the CAM systems just started to allow you to support multiple setups, visualize them, and simulate them. But you are still left alone. There is no proper assistant for work holding and job setups, etc. So that's a big gain.
I never thought about this until just now, but my sort of journey into the CAM world started around 2020. I cammed a few things before that, but not much. And so I just sort of take for granted that a Deburring toolpath and a smart chamfer toolpath exist. In Toolpath, capital T Toolpath, we struggle a lot with like non-machinable chamfers. People will, it just happens all the time. You just model the chamfer like straight into a wall or straight into a corner, right? And then machinists just sort of either know how to do what you talked about with projection and trimming, the old school way, or the way that I do it is I just put the smart toolpaths on it and let them go. And I guess I take for granted that that's just how it works now. But if I was camming in, 2005 or something, then I would have been doing all of that work. So the next time I get frustrated with my cam system, I'll have to give it a little bit more of a credit, I guess.
Yes.
But yeah, that's the amount of automation that has come in is astounding. I think the irony is that with that increased automation and increased capability of the cam system, the engineers on the other side of the table just make the parts more complicated.
Yes.
So we seem to have like a conservation law going into effect where like the more capable our machines and our cam systems get, the more complex our parts get. And so a part still takes about 20 minutes to make, no matter what kind of thing. So that's an interesting side note.
But in reality, the machines are just sitting there waiting for parts to be machined, right? There is a survey from a large machine tool vendor. They say that they have online connection of their machines to their facility. And then they say the customers are utilizing the machines around 1,000 to 1,500 hours per year from the 8,000 hours, right? Which is possible. So that means if you could program automated using Toolpath AI algorithms, and then you do machine tending, and you would do maybe some in-process monitoring like you do with Chatter, right? You could get there. You could maybe increase the utilization much further.
We have to lower that barrier, though. And so I'm going to pitch an idea for you to think about. And maybe we could talk about how you would think about building these toolpaths. But the cheapest automation out there is spindle gripping automation. And I don't know if you've seen it recently, but there's one company who's combined a spindle gripper with basically built into the machine pallet loading, where they use the moving head of the machine to go and grab the pallets and things like that. I think that if CAM systems could support spindle gripper toolpaths, that we would see an explosion of adoption of automation. I think it's very, very challenging for most people to imagine writing their own macros and iterating around all of that stuff. But if we could just put in a toolpath and say, here's your spindle gripper and here's where the part gets loaded and here's your matrix that I need you to pick from and go, that would fundamentally change the game. So there's my pitch for ModuleWorks to start making spindle gripper toolpaths.
Yes. It's on my to-do list since you pitched that idea to me. So I will talk to these people and get a hold of a gripper, because we have our 5X machine here. So I would like to get this integrated such we can prove out that concept. The thing is, we did two preparations for making things like that. The first one is, typically if you machine something, you use a rotating tool, right? So you have at the end so-called 5 degrees of freedom. But if you do things like if you cut something with a chainsaw on a wood router, then you have 6 degrees of freedom. So basically, the gripper is a 6 degree of freedom problem, plus the gripper opening and closing may be another degree of freedom. So basically, the software architecture needs to cope with that, right? So basically, imagine that now ModuleWorks is supporting fully 6 degree of freedom toolpaths, right? That's what we do because we serve also the wood industry, etc. But we need to make our partners, the CAM companies, to support also in their databases that the toolpaths can be 6 degrees of freedom, right? So we need to introduce signals that opens and close the gripper at the same, etc. So basically, the fundamental toolpath is not there the big issue. I will explain that a little bit later, how we attack that as well. But the issue is more how you integrate it into an existing CAM legacy infrastructure if their framework is not designed to support that, right? So they might feel, okay, it will require a lot of change and regression. So should we do that? It will increase the memory footprint of all toolpaths if we have another field or something. So they need to redesign it and so on. So these are the challenges, but that shouldn't stop us, right? So I think we can pick some partners who wants to be the first movers in that and then generate some attraction. The second topic was for us, anytime when we develop a new toolpath, we had to start building something called the pipeline for this new toolpath, which consists always like analyzing the part and the initial toolpath and collision checking and linking and checking against the stock, etc. So all this pipeline needs to be reviewed for each new toolpath, and it was always a big effort for us to come up with a new toolpath. So even if the toolpath was just drilling a hole, we would maybe spend a few weeks just to configure the R framework to start coding a new toolpath, right? Because we have to review all the stages, because we are very object oriented, but still a pipeline based, etc. Now we have a development activity which allows us, the goal is there to make this such abstracted that if you want to develop a toolpath today, if you know what you want to do, you could just spend one day and reuse everything we have and come up with a new toolpath, right? So the goal is, can we make every single developer of ModuleWorks being able to develop a toolpath strategy per day if they know what the toolpath should be doing? Of course, the toolpath itself can be complex and we can spend weeks and months. But in terms of reusing the 2000 man years of code and just using the bits all there, like the linking and clipping and collision checking and identifying of the features, etc., all these things, if you can reuse everything and spend just a day to do the delta, to do what we want to do, then I think we can also easily try this toolpath for grippers and other things, because then we can only focus on that problem of, okay, how big is the part after machining, where I can hold the part, how I need to grip, how much I need to close. But that's just one toolpath. At our visit to John Sanders, I also got a very good idea for also a toolpath which doesn't even require 6 degrees of freedom. So it's much more straightforward for integration. So I hope that we will have some good news on this topic as well.
I'm looking forward to see that toolpath. We'll leave that one as a surprise for our listeners, though. Other than the new toolpath that you thought of at Saunders and the gripper idea I just gave you, are there any other new toolpaths on your mind that you would love to invest some time into?
The biggest investments we do is we would like to support you guys working on automation with AI much better. And the way we would like to get there is we would like to find out what are the CAM programmers today deciding left or right based on something. And we would like to attack this by using the context of what the people are doing. So for example, if you have a strong work holding or a weak work holding, or you have this material or that material, you have maybe a machine with a limited workspace, etc. So how we can give you a toolpath which is perfectly tailored for the machine, for the setup, for the fixture, for the remaining stock from the previous operation. So basically all these things that are happening at the level of CAM operator, and then you would solve it with AI and with some solutions from recipes on your end. We could take over a bit more responsibility and ease up your work, that you can focus more on the orchestration of this. And then all the exotic bits, like if you have very thin walls and very difficult geometry, maybe a very fragile part, nobody would expect a very complex, fragile part to be machined with your AI algorithms. But you can do the planning, but you need to treat that part differently than other parts. But I could do that at the toolpath level if I know the context, right? So basically the biggest job I'm doing is how we can increase the awareness of the part geometry and also the machine, the environment, etc. And the same goes with the tools. Like if I'm using a tool from that manufacturer, how it machines a particular material on a spindle having that horsepower, right? And these kind of things are things that we would like to cover to roll you the red carpet for doing all the AI magic you do.
You know, you talked about this a little bit very briefly earlier, but as I've gotten more and more into surfacing and 3D machining, one of the things that I didn't appreciate early on until we started having to deal with the computational geometry was how much harder it is to deal with non-ball end mills computationally. And it shows up in all kinds of weird places, but like checking for collisions is much simpler when your tool is a ball end mill versus a bullnose end mill. And Scott Moyse recently pointed out that like 3D surfacing with a bullnose end mill it's more computationally expensive. The results can sometimes not be as good because the calculations that you have to do to make sure that that tool has the right contact angle and isn't hitting the surface anywhere are much harder. And now we have circle segment tools, which you also mentioned, you know, lenses and barrel cutters. And those tools make it even harder. But some of the most efficient ways to either improve your runtime or get a better surface finish are these circle segment tools. But finding the right tool for the right surface and then getting a good toolpath out of it can be very, very challenging. And I think for me, it was surprising to realize just how much of a challenge non-ball end mills are. But also on a similar note to that, how much of a challenge it is to get a good toolpath with good point spacing that will work well with the control you're running on. So like the same exact geodesic toolpath in Fusion, for example, when you push it to the Haas control versus a Fanuc control versus Heidenhain, you could get very, very different results. And so I know that inside of ModuleWorks, you've put effort into like giving point spacing control and trying to give enough control to the user, to like the guts of the toolpath, to tailor it to their control. But I wonder if in the future we could have more smarts in the toolpath where it could understand, okay, I'm going to this control or that control. So here are the combinations of settings that give really good results.
Absolutely.
Or if maybe in the future, maybe the controls need to evolve to accept like a higher level toolpath, and then they can discretize it themselves potentially. But
yeah, you are right. I mean, that's one of the biggest problems there is that the G code is linearized, right? So you have linear segments. If you are lucky and you have an exact arc, you can cut an arc. But other than that, you linearize everything. So if you end up having a freeform shape and a tool, ball nose or bull nose or whatever, or circle segment tool, then you end up getting a lot of small segments, right? But at the end, the people want to have a smooth, nice surface. They would like to have a smooth surface. And sometimes the accuracy they need on the surface is much different than the smoothness of the surface. So what we call is the RA value can be much different than the dimensional tolerance, right? And so what happened is in the past, control makers, because they had also limited capacity, they were also running 386 and 486, etc. They relied on some point spacing. They did some magic called compressions. They smoothed things, etc., which caused other problems. But sometimes they smoothed the wrong corners, etc., because they don't know even if they cut the left or the right side, and so on. So that created a lot of legacy that controls started to do some messaging of the data that you feed in, right? And there was an initiative that people would start using Nurbs on CNC controls. We developed a Nurbs-based output, and CMAS control was able to support that. CMAS was propagating that a lot to their customers. But it became a niche because not all CAM vendors adopted that, and not all CNC vendors adopted that. But it was exactly giving a good answer to that. Nowadays, luckily, the computers are much faster. The CNC controls have much more horsepower, so they don't have any issues with millions of segments, right? So today you could run a several million toolpath with very small spacing and still expect the control to cope with that. So it would not drop the feed rate like 10 years, 20 years back, right? So that opens some doors, but still you need to tweak the right smoothing tolerance of your control, etc. So there are a lot of issues around that, and there are no easy solutions to that. I think as the computers get faster, people will end up creating toolpaths with very small tolerances, like putting just a micron to get a good finish. and then turn off the compressions, smoothness of the CNC control, and just trust that it will do the job. But that's a journey, right? There is no standardization how controls message the data. And so what we try to do is we work on something called superfinish, where we use the Nurbs quality data at nanometer accuracy and then generate extremely high quality 6-digit after comma in millimeters. So basically nanometer accurate toolpath output with density, and then try to generate extreme high quality surface if the machine is capable of doing that, and trying to establish this as standard for freeform machining, because CNC machines got really better and there are very good tools that can machine. So there is a chance of getting mirror finish from a decent CNC machine. You don't have to have the top brand CNC machine to get that, like 10, 20 years back. But you need to orchestrate the CNC control, the machine, the CAM system, the data transition and everything. So we are working on that. But I think for you, the ideal would be that you could just tell us, okay, this is Heidenhain, this is Fanuc, this is Siemens, this is Haas, and we would just give you the toolpath. We believe the control would do the best out of it, right? I think that would simplify the problem.
You know, it's a little wild to realize that, like, what most controls run off of, not all. I know Heidenhain has their own language now, and Datron does as well. But like Fanuc and Haas and Brother and all of them run off of G-code, which literally dates back to the days of tape. And like the language is developed to run on tape. And so we've somehow managed to, in quotes, standardize, right? Because everybody's G-code is different. That's why we have post processors. But somehow we've managed to standardize and like almost calcify as an industry on this like extremely dated language. I know Heidenhain has moved past that, and Datron has as well. I don't think Siemens has. I think they're still using pretty standard G-code. So that is another very interesting point. Like, again, we demand a lot of our CAM systems, and then we take all of that extremely complex math and shove it through a 1960s era straight line and circular segment programming language.
Yes.
Yeah. Okay. Finishing up the trip down history lane, I find it interesting that your first foray into this had to do with slicing. I didn't realize that you were slicing into Nurbs, which is really interesting, especially because like when you try and slice surfaces with Nurbs, like they become like extremely high order polynomials, right? Like 32 dimensions or something, which today is not a big deal, but dealing with that efficiently on a 486 must have been a challenge.
I think the trick was instead of running a numerical solver just to solve it for one slice. So, you know, if you have 2 blocks of cards, you would do this, right? You would bring the cards like that. Mm-hmm. So I was doing the same. So I had hundreds of surfaces here and I have hundreds of planes to slice. So I find a way to create objects of it and let it slice each other at the same time. So basically, I was not solving the polynomial just for one slice. I was solving it for all of them at the same time. So I think that was the trick to get it there. And at that time, it was okay, the speed. Sometimes people calculated several minutes. But after 30 years, now, if you use my Nurbs toolpath, it's almost instant, right?
That was in the 90s, you said, right? So about the same time, actually maybe 10 years before that, the graphics industry was being developed specifically for like medical imaging. And so a lot of the technology that we rely on today for meshes and Nurbs and all of that geometry actually came from a desire to process like CAT scan data and X-ray data and MRI data. So I find that as a very interesting intersection, that like the foundations of computational geometry that we all take for granted today actually come from the medical industry. So I think that's cool. So we went from medicine to computational geometry, and then using that in CAD/CAM. The kind of Newton solvers that you built, I actually also built Newton solvers for aerospace and finite element and CFD applications. And now we're coming all back around to CNC and CAD and all of that stuff being used to make parts for aircraft and MRI machines. With, frankly, sometimes insane tolerances. Like you said, people are producing like optical quality finishes straight off the machines nowadays. and the pipeline of things. I've never really thought about that before. Like, it's when you talk about optical quality finishes, you think about like machines with linear actuators, diamond tooling, very like how much precision. But even just down to like the quality of the G code you're outputting, and then the interaction between the Toolpath engine, the post processor, the G code, the control, and then all the way down to like the ladder logic and the individual board controls. That chain of convergence, just in quotes, just to get a mirror finish is, I don't know, I've never thought about it before, but it's kind of mind blowing now. And honestly, until this moment, I sort of took for granted that, oh yeah, if you just throw sort of tons of money at a CNC machine, it'll produce mirror finishes, without really thinking about how many layers of technology have to collaborate to get there.
Absolutely. And the good news is, Justin, that there are so many CNC machines out there who are just capable of doing mirror finish or almost close to mirror finish, but they just require the right set of CAM software and parameterization and the data and the tools and so on. So basically, we could activate a lot of things to eliminate people doing manual polishing, right? So there are organizations in Germany where they save in the next 10 years maybe $1 billion just to eliminate the manual post-processing work on the part, like in automobile and so on, where people need very high quality results. So that's an opportunity, and that's exactly what we got with deburring, right? Deburring was just a very simple toolpath that we introduced. It was appreciated very well in the industry, and we heard stories like, okay, there is a shop with 80 people doing in India only deburring manually, and once they have our software, they just press the button and it just works out of the box. So they put these 80 people to the assembly line, such they don't have to do manual deburring, right? So basically, such things can be an extreme time saver, and it's just sitting there, right? So people didn't bought new machines for deburring; they just used their existing 5-axis machines. I think there is a lot we can do with these multi-axis machines. If we, as you said, the gripper, for example, just do the gripping, then you create multiple parts overnight. You can run your CNC machine the whole night if you just use a gripper and put the part aside, right?
I think that brings us to a pretty good place to wrap up, which is we're starting to look into 3+2 in Toolpath. So Toolpath only does 3-axis right now, but we're starting to push into 3+2. And I very commonly say that 90% of machining out there, of 5-axis machining, is 3+2. But nowadays, I have to add an important caveat to that, which is except deburring. Because even on the simplest 3+2 parts, the deburr toolpaths, the part is moving all over the place. And again, I think we just take that for granted now. But, if you rewind the clock 5-10 years, like simultaneous 5-axis motion, like the kind we get on deburr toolpaths, was not an easy thing to program. And you looked like a real hero if you were doing demo programs for trade shows for that kind of stuff. And now we just throw a toolpath at it and enjoy watching the parts spin around. Yeah, that's amazing.
And it was also a very enjoyable journey for us with deburring, because we had just this 2,000 menus of code sitting there doing all this complex collision checking. We said, okay, we just use the same, it should just run on the edges, right? It should do the same collision checking and so on. So basically it was, for us, not a big step, right? But if you would take all the things which are there, it's easy. If you need to start from scratch, right, then it's a big task.
Well, I think that's really impressive that you guys have started sort of building your pipeline out in a more abstract level. And hopefully that will lead to more and more innovation in the toolpath space. All right. Well, this was super fascinating for me. Thanks so much, Yavuz. Is there anything you want to add before we wrap up? Anything you want to preview or talk about what the next big toolpaths you think you'll be working on are?
Yeah, maybe one last anecdote before we wrap up. So as I said, it was mid of 90s, slicing geometries to generate 5-axis toolpaths. And then we came across a very interesting company in Netherlands. They are good in shipbuilding, and they had a research company just focusing of building of these 500-meter tankers, just 20-meter models on a gantry machine. And they were stacking up wood plates on top of each other and gluing them.
Okay.
And then but they would have a stair-stepping, effect. And then they would use a 20 millimeter cylindrical cutter on a gantry just to machine the surface. And they were using our 5-axis algorithms. They were generating slices and just doing the job. And they were happy with the solution. But then they come to me and said, okay, look, at the tip of the ship and at the bottom, they have complex shapes, and your slicing parallel, delivers some not good results there. Can you do something better? Can you give me a toolpath that would just go along the geometry so it would be morphed, right? And it was a tricky moment because I didn't have any solution. I didn't have the geodesic toolpath at that time, right? I knew the geodesic is going to be but I knew that geodesic will take years to develop. So then I thought about it, and I just in one afternoon, I had the idea that instead of slicing with the planes, I should slice it with some non-planar planes, right? So basically curved planes. And so I defined an implicit space definition of non-curved planes, let's say, and just used the abstraction I had because everything was object-oriented since the 90s. Just change one code and said, okay, instead of this class, use that class. The plane is not planar anymore. The plane is curved. And all the mathematics just did work. I had in the afternoon the morph toolpath, which became the biggest success of ModuleWorks at the beginning of the company because nobody had these morph toolpaths, right? So it was unimaginable. It was not the true geodesic, but it was morphed, and nobody understood how these morph toolpaths would work, right? And everybody started to machine fillets in 3-axis, 5-axis with this morph toolpath. It became a huge success, and there was just one customer asking the question, so if you have your software architecture right, and then you have the right ideas, understand the application needs, you can be extremely productive in software development. And I see the passion, the competency, and the motivation in your team eyes. I mean, you are doing a great job. So I'm wishing you all the best and success for Toolpath to succeed in automating the CAM programming.
Well, thanks, Yavuz. I think to wrap up, what I'm hearing is that we need to make sure you spend some more time inside machine shops.
Yes.
So I'm going to do my best to get you some invites to watch people program and see what other non-planar plane ideas you can come up with.
Yes.
All right. Thanks so much, Yavuz. It was great talking with you.
Yeah, it was my pleasure, Justin. Many greetings. Bye for today.